Good afternoon, everyone. As Farshad was so kind to mention, my name is Cole Spencer. Not doctor yet, working on that, but I appreciate the honorific anyways. As we're all here to talk about today, we're looking at ground bottom ash and concrete. Really glad to see so much interest in this topic today. We've had really great turnout. And thank you again, Farshad, for organizing the session. I think this is really great. Oh, I need to click first. That's right. There we go. Okay. So first, we're going to talk about a lot of stuff you've already heard in the first session. Bottom ash and fly ash, what they are. And we're going to talk about the sources that were gathered for this study. So as we've seen in a lot of presentations, difference of bottom ash and fly ash. Well, fly ash is what we collect from the particulate collection systems at the end of the combustion process, whereas our bottom ash is first a molten slag that's collected on the bottom, the sides of the furnace, that's then removed and quenched and crushed for either disposal or for use in road base or some other applications. So with all this in mind, the same sort of questions you've seen in many other presentations today. First, can bottom ash be made into a usable ASTM? If so, is it reactive in cementitious systems? And then also, how does it compare to fly ash, a material that we have a lot of institutional knowledge about? So for this work, we obtained fly ash and bottom ash from 9 different facilities across the United States. The geography doesn't necessarily matter here. It was more about selecting sources that show a range in calcium oxide content, looking at the calcium oxide content of the fly ash, and then seeing how the chemistry is reflected in the bottom ash. So on that same note, a little bit of discussion on the characterization of these materials, these 9 fly ashes and bottom ashes. Now, talking about bottom ash, like we've heard a lot before, in terms of physical characterization, the main thing we're worried about is processing. And in this case, processing meaning milling or grinding. As has been pointed out, the words ground bottom ash, milled bottom ash, they're used kind of interchangeably. I might myself go back and forth, so I hope you'll be patient with me in that regard. So we took our materials that many of them resemble the gradation of aggregates in some cases, processed them in our laboratory ball mill and ground them into a usable powder. Now, because of the amount of materials sourced for this, to make comparisons a little bit easier for the processing of these materials, we decided to stick to a ASTM C311 fineness of 10 plus or minus 1%. And just to be clear about the terminology here, because it can be a little confusing. The ASTM C311 fineness test is a wet sitting process on a 325 sieve under constant water pressure. So when I say a fineness of 10 plus or minus 1%, that's referring to the mass retained on that 325 sieve. So somewhat conversely, a higher fineness by this measurement means higher percent retained, which actually means a coarser material. So I'll try to be clear with my language as we go forward. So when we consider the results of these powders, first we're going to look at the particle size distributions of the fly ash. You notice a few things. As is typical of fly ash, you have a bimodal distribution, which favors the finer mode of that distribution. And also, as these fly ashes were not processed in any way, they were used as we received them. And also, these fly ashes are standard production fly ashes. We have a wide range in particle size distributions. Our bottom ash, on the other hand, of course, because we prescribed the grinding regime, are very similar to one another. You still end up with a somewhat bimodal distribution. However, that distribution is much more uniform. And for example, if you were to look at about the 100 micron diameter size and compare those, you see that we have less coarse content in this ground bottom ash, but also we don't have that same favoring of the fine mode. So essentially we end up with a more uniform distribution, but also a tighter distribution. Things to keep in mind when we start comparing the performance results of these materials. Now, in terms of the morphology on the microscopic scale, we see similar images that we've seen multiple times today. We have our nice spherical, pretty uniform fly ash, whereas our bottom ash is obviously visually more crystalline. What's kind of interesting, though, is if you were to look at this picture, you see more than just your standard sort of crystal granular shapes. You also see maybe perhaps some fly ash spheres sneaking in there. You also see particles like this one that appear to have some amount of glassy, amorphous content. And so wanting to look at that a little bit closer, if we take this same bottom ash source and before it ever hits the ball mill, you just sieve it over a number 100 and look at the fine particles before it ever gets ball milled. You see an interesting combination of different types of particles. You have particles that look like fusions of multiple fly ash particles, or perhaps fusions of fly ash particles with just more general amorphous glassy structures. I wanted to point this out because there's reasonable concerns about, as we've heard today, perhaps using reclaimed ashes that have commingling of bottom ash and fly ash. People are concerned that do these constitute significantly different materials? Well, it's interesting to note that essentially bottom ash does have fly ash in it. We just tend not to see it in this form because it's run through a mill first. This table is way too big and there's way too much data, so we're going to do it in chunks. I'm going to show the bulk oxide content of, as determined by XRF, of these fly ashes and bottom ashes from each of these different sources. And so again, way too much to process all at once. So we're going to take it bit by bit. All right. So first, in terms of what we care about from 618, the governing standard for fly ashes, we tend to care about the sum of the oxide content or main oxides, which refers to the silica, alumina, and iron contents. In general, I'm going to be saying in general a lot, by the way. In general, we're seeing that our bottom ash content, our bottom ash has higher silica and iron contents, but lower alumina contents. But overall, the sum of the oxides in general is higher in our bottom ash than in our fly ash. Now, when we look at calcium, again, this is what governed which sources we selected. I wanted to choose a wide range of calcium oxide contents. We see a nice range from 2 to about 30% in our fly ash. We see that our bottom ash doesn't match in a lockstep. We see that our bottom ash tends to have slightly less, but that difference becomes more exaggerated in our sources that were a higher calcium fly ash. So what I mean is when you look at the lower calcium sources, they're actually fairly close to one another, but that difference grows with increasing calcium content. And then in terms of the other minerals, or excuse me, elements, for the trace elements, it's pretty inconclusive. It bounces around and we're talking about very small amounts. More notably from this last group, we can consider the sodium equivalent, the sodium content plus 0.658 times the potassium. And in general, we see lower sodium equivalent content in our bottom ash than our fly ash. Of course, as has already been noted in the previous session, just the alkali content as measured by XRF doesn't necessarily tell you about the availability of those alkalis. It's just an interesting trend to observe. The last bit of characterization we're going to talk about today is the characterization per ASTM C618. Currently, 618 applies to production fly ash. It doesn't pertain to bottom ash. However, there are ballot items working through ASTM at the moment trying to add bottom ash. So likely very soon, these will be directly relevant results. But first, we're going to talk about the fly ash. Again, as was decided, a nice range in calcium oxide content. The other two chemical requirements that are present here that haven't been shown yet are your moisture and your LOI. Moisture is more of a process-dependent variable. It's not necessarily something intrinsic to the material itself. LOI tends to be a representation of non-ignited material, which tends to be related to carbon. People care about that for air trainers, as we know. And again, these are regular production fly ash sources, none of which cause any issues, which is what we'd expect from fly ash we're expecting to sell to the market. In terms of the physical requirements, we see from this fineness results, again, the same fineness test as described earlier, that C311 sieve-based fineness. We're seeing a wide range in results, which mirrors what we saw in terms of the wide range of particle size distributions of the fly ashes, right? From about 10% all the way up to 29%. The only real performance test, if you want to call it that we have in 618 at the moment is the strength activity index test. We could have a whole session on people's concerns with the strength activity index test. But when we consider the performance of fly ash in this test method, the two properties that people tend to consider that contribute to their performance are the particle size in terms of their fineness and the calcium oxide content in terms of the latent hydraulic reactivity of these materials. And as we can see, those two variables did significantly impact our strength activity index results, where our sample with the lowest calcium oxide content still scored over 100%, likely due to its fine particle size with its 14% fineness, whereas our high calcium oxide content samples in sources 7 through 9 both have a high calcium oxide indicating latent hydraulic reactivity, and a few of them also are quite fine as well, which happens a lot with Class C fly ashes. Now, if we consider this same characterization regime for our bottom ash samples, again, as we already saw, the calcium oxide content does have a range, but not as wide as we saw with the fly ashes from those same sources. Notably that there are two samples that do fail the LOI requirement. This happens sometimes with bottom ashes. It could be evidence of uncombusted coal or just latent carbon. In terms of the physical requirements, again, the fineness was prescribed in the milling. So we hit that 10 plus or minus 1%. That's obviously to be expected. The interesting thing though is when we look at the strength activity index data, now that we've controlled for fineness, if we apply that same previous knowledge of how calcium oxide affects fly ash performance, we're not seeing as obvious of an impact on our strength activity index data. Arguably, it does trend upwards a little bit, but it's easy to cherry pick certain examples like our source 8, where the strength activity index barely gets around 80%. That sample had 22% calcium oxide. We had a fly ash with 22% calcium oxide that scored over 100%. So it starts bringing into questions similar to what we heard from Larry Southern and others. Is the calcium oxide content in these samples hydraulic in the same way? Or is it just evidence that you're having less amorphous glassy structure and it being replaced by a crystalline calcium oxide? In terms of material performance, we have two types of data to look at currently. First is going to be our 1567 ASR mitigation. This is a accelerated mortar bar test using a higher temperature curing, natural reactive aggregates, caustic curing solution. And with concrete, we have compressive strength data, early compressive strength data, and resistivity measurements. Now for ASR mitigation via this test method, we're going to look at how our expansion decreases as we increase our replacement level. Of course, we have to consider the fact that our expansion will decrease just due to the dilution of the cement in the system with increasing replacement level. And as the graph populated there, it populated in order of the fly ash source, which again relates to the amount of calcium content than the source. And so in general, we saw, not lockstep, but in general, higher calcium, higher expansion. We also see a very wide range of performance, of mitigation performance in the fly ash samples. Whereas if we look at the bottom ash in the same way, again, we generally see an increase in calcium showing an increase in expansion, but we see a much tighter range of performance. This is likely related to the very tight range in particle size distribution. So if we consider that, perhaps this is more evidence, well, there are similar particle sizes, and earlier the strength activity index called into question exactly the role of the calcium oxide, and yet we are seeing notable difference source to source. So perhaps, again, is it the calcium oxide participating in some way? Is it just an indicator of less pozzolanic material, amorphous glass in the structure? These are some questions that need further addressing. In general, it's interesting to note, however, when you look source to source, our ground bottom ashes processed in this way, in general, perform as good, if not better, than the fly ash from the same source. That being said, we're not seeing a huge difference, right? We're talking about materials that are definitely in the same ballpark to one another. Right? We're not, these results don't indicate this to be a significantly different type of reaction or a different type of material. In terms of the concrete testing we've done so far to decrease the amount of mixes we are working with, we selected 3 of the sources, one to capture a low calcium, one to capture mid calcium, one to capture a high calcium source. Concrete was set at 2 different replacement levels, 20 and 30% with these. And this is just a repeat of a summarization of some of the data we've seen so far. So again, we've captured the range in calcium oxide content of the fly ash. Our finenesses are very different in the fly ash, as to be expected. We also see a fairly broad range in our strength activity performance as compared to the range you see in the bottom ash sample selected. In terms of mix design, this isn't all that interesting, with the exception to say that mix design was chosen to meet the GDOT Section 500 Class A general use concrete. So we went with a 620 pound mix, sticking to the max allowable water cement ratio of 0.49. The most interesting or useful piece of information to gather from here is that in order to hit the required slumps, we varied our water reducer dosage. And by doing so, you can directly see that in both the fly ash mixes and the bottom ash mixes, we required less water reducer to hit the same slump range, which is important to note because there are concerns regarding the angularity of the material if you'd still get the same water reduction benefit as you do with fly ash. Not as much, and obviously you gain the benefit of using less sand by introducing it, but it still seemed to give you a moderate water reduction effect. Now this is early data. Unfortunately, we had some COVID-related delays in the lab, so I only have 14-day data to show you. So this is just general information. More substantive conclusions are to come. They're grouped by the source, the calcium oxide content of the source. We have the 20% mixes first and the 30%. Way too much on one graph, I admit. But the most interesting things to note here is that between our fly ash and our bottom ash, for our low calcium sources, we're seeing very similar strength development. It's maybe slightly improved strength gain development, but really, again, too early to say. The main thing to take away from this graph is the difference in performance of the high calcium sources in terms of the fly ash and the bottom ash. We're seeing much less strength development in our high calcium bottom ash source than the fly ash source. Now, again, because of the differences in the calcium content between the bottom ash and fly ash from the same source, the fly ash here has about 28% calcium oxide. The bottom ash is about 22. So there is a difference there, but we wouldn't expect that 6% difference to account for that difference in compressive strength. We also have resistivity data via Winter probe, and we're seeing similar performance results in terms of the low and medium calcium oxide content sources. Again, we're playing in the same ballpark here, but in terms of the resistivity of the high calcium fly ash sources, we are seeing a difference where instead of this huge gap between the performance of the fly ash and the bottom ash, we're seeing them much more closely related. Oh, I forgot to do that fun little animation. Okay, so I know that was a lot of numbers up on the screen. I know that was a lot of graphs with too much information all at once, but what are some broad scale conclusions we can bring from that? First is that bottom ash can be used as a supplementary cementitious material. It can produce good usable concrete and provide evidence of reactivity, provided that it's processed appropriately. We saw on here, we only ground to one particle size distribution level, but we've seen a lot of other results so far that show the impact of how much grinding can change the apparent reactivity of these materials. Additionally, we see that the performance of bottom ash and fly ash are within the same range, right? They're not different enough to perhaps cause too much confusion or harm, because a big question, as we've heard repeated a lot, is what about reclaimed ashes in the future that have commingled bottom ash and fly ash? What about blending these materials in the future? What we're seeing is results that are within the same range, such that hopefully that alleviates some concerns. And I think a lot of the data we've seen so far today indicates that as well. In terms of future work that's going to be done with these samples, obviously some later age concrete strength and resistivity data. I'm sure you'll see that more at a future convention when we have it. We want to better understand exactly what's going on with this calcium oxide. Something that I didn't include here for time, but I know was asked in a question in a previous session about what phases calcium is present in. With some preliminary XRD results, we're seeing what everyone else has said, that we have lower amorphous content, higher crystalline content in our bottom ashes compared to the fly ash. And there seems to be, in our higher calcium sources, high content or high amounts of akermanite and diopside, which appear to be the crystalline phases that are capturing those calcium oxide materials, thus making it less reactive. And then finally, there's more research that's needed into that relationship I described earlier between processing, grinding, and performance, because there's interesting work to be done to determine what kind of performance you can get out of these materials with advanced grinding, or perhaps balancing energy consumption with performance to meet your needs as an engineer or as a specifier, while also being concerned and cognizant of emissions and energy consumption. And that's it. Thank you very much for listening.